Hello and welcome to this presentation, Condition Monitoring is Not Enough. My name is Jason Tranter, the Managing Director and Founder of Mobius Institute. In this presentation we're going to just quickly summarize condition monitoring and the benefits of performing condition monitoring and its traditional role, and then we're going to look at not only detecting faults but how we prevent them in the first place. We'll look at root cause failure analysis. We'll look at using condition monitoring as a quality assurance and quality control process, and then we'll look at how we go beyond just condition monitoring to condition management, and we'll explore the topic of defect elimination. Very briefly, just so you understand where I'm coming from, I've been involved with condition monitoring since 1984, and that was, a variety of roles, from running my own company in Australia to working for a company that developed condition monitoring systems to starting Mobius Institute, which is involved in providing training in the area of condition monitoring. So, our business has been going 15 years, and over those years we've developed various training courses and so on related to condition monitoring and reliability improvement. Particularly in more recent times, we've taken our reliability improvement ideas and put them into a product. The point I'm really trying to make here is that over those 30 years, I've seen a lot of companies try and run successful condition monitoring programs, and a lot of companies really struggle to really run their condition monitoring program as well as perhaps they should. And they're not getting the returns that they'd hoped from condition monitoring. And we'll explore a couple of those points as we get through this presentation. The other major observation through this time is that most people really focused on detecting faults and providing a warning that a machine was failing, but not necessarily focusing their attention on the area where they would get the greatest return on investment, and that is on eliminating the root causes of those faults that they were detecting with their vibration analysis systems or infrared systems and so on. So, a little more about us. We do have training centers in about 50 countries around the world, and we have offices in a few countries as well. I am located down there in Australia, and that's actually where our headquarters exist. So, condition monitoring. What we're really trying to do is minimize risk through early fault detection. And as you're probably aware by now, condition monitoring, our rotating machinery and electrical equipment and other process equipment give off a lot of telltale signs that there is a problem developing, and if we catch those signs in enough time, we can then react to them. There are lots of ways we can do that. The traditional vibration analysis, ultrasound, thermography, and you can see other ones listed there. There are a lot of techniques that we can use, and it depends on the type of equipment we're monitoring and so on. In my discussions about condition monitoring, I would include inspections and observations as being both an important part of condition monitoring, but some people might consider them just normal sort of maintenance tasks. But in general, if time is being spent to inspect a piece of equipment to determine its condition and the necessity for maintenance work to be performed, corrective actions or whatever, that to me is still basically condition monitoring. We're monitoring the condition so that we can react, and that's a key word here really. We react if there's a problem detected. And performance monitoring certainly fits into that. If we can see that the pressure or flow is not adequate, well, that's a condition that needs to be remedied. Okay, the basic principle behind condition monitoring is that we will run for a certain period of time when the equipment is running in its normal, healthy state. And we could say that, it's running defect free, but let's just say that the defects in the system, the inherent unreliability, if I can put it that way, hasn't yet caused any faults to begin to develop. Now, at a certain point, and this y-axis here is condition, and depending on different people's definitions, we might show that the condition has actually degraded a little up until this point. But at a certain point, we can say that there is the ability to detect that the condition is degrading and that a fault has developed, albeit minor at that point. And from that point on, which we call the P point in the PF interval, we can use these various technologies to detect that there's a problem. Now, I've put ultrasound first. In some cases it would be the first to detect it if you had the ability to pick up, say, a lubrication problem. But generally speaking, a bearing becoming loose or becoming hot and making sound, that is a late stage failure. Other technologies are going to pick it up earlier, but of course it depends on the failure mode and the type of equipment. What we really want to do is pick it up as early as possible. The earlier we pick it up, the lower risks associated with the equipment and the lower cost of dealing with the problem. We have more time to plan it when it is convenient for us to deal with the failing bearing or whatever the problem is. But certainly the longer we leave it, we're increasing the risk of failure, we're increasing the costs to deal with the problem, and we're getting less time to plan. But that's the core principle behind condition monitoring, and as long as we take enough measurements to at least plan to take 2 within this PF, F being the functional failure, if we plan to be taking 2 measurements in that period, then we should detect it and be able to respond. We may take more measurements during that period, and that gives us a higher likelihood of detecting it earlier. And then the other key is to use those technologies properly, but that's not really the point of this presentation. So, what are we doing with condition monitoring? It is there for fault detection, not when it has catastrophically failed, of course. We're trying to get that early warning. We can use that information to improve our maintenance planning. We can avoid secondary damage or collateral damage. If the bearing failed, maybe the shaft would be damaged as well, or a seal would be damaged, or there's secondary damage, and we get to avoid that. If we're doing a good job, we can reduce our inventory of spares because we have more confidence that we will detect it early enough that we can perhaps order the spare that we need, the replacement piece of equipment that we need or part, and we know we have enough time to get that into our stores. So rather than having it on our shelves, which is costing us money, and there's the potential for that part to degrade over time, we get to save some money. And there are fewer safety incidents as well, both in terms of the equipment failing, which can have a ripple effect both from a safety and environmental point of view, but because we can plan our maintenance better, we'll have more time to plan the maintenance and we'll have a better idea of what's wrong with the machine. There's less time spent with the machine, and that reflects improved safety situation. But the question is, what does all of this have to do with reliability? Most people feel, well, condition monitoring, and I'll put the emphasis on the word monitoring, does it improve reliability? Well, certainly if you look at it from the point of view of, are we having as many failures as we used to? Is that your sole measure of reliability? Well, from that perspective, yes, we improve reliability of the plant. We can make plans because we have a higher likelihood of having less downtime, greater availability, and so on. But are we improving reliability? What have we been discussing so far? We're really managing failure. We are detecting problems or fault conditions that for the most part just should not exist. Okay, if you've been running the machine for the last 15 years and finally we detect a bearing fault or something, we say, hey, it did a good job. We're happy with this situation. But that's usually not the case. It's not 15 years later that we're detecting a problem. It is much sooner. So we're either letting it fail, and we might choose to do that because of the criticality of the equipment or the demand on production. We get advanced warning of the failure, and we hope to fix it before it fails. But the emphasis is on failure. And so even though we like to talk about reactive maintenance, being separate to condition-based maintenance, it's pretty easy to actually call what we're doing reactive maintenance. Sorry, it's just that we're reacting earlier. So, if you think about the PF interval that we looked at before and the failure we had, what we really want to do is have the machine run in this area for as long as possible. We want to delay the onset of failure as long as possible, which includes a reduction in infant mortality. Now, this presentation isn't about random failures and infant mortality and so on, but that's ultimately what we want to do. And we also want to detect the failure as early as possible. What we really want to do is keep operating the machine in this defect-free state. So instead of detecting the problem after 6 weeks or 6 months or 18 months or something like that, we want time to just keep passing. Now we perform our condition monitoring at the correct rate because we don't know when this fault is going to occur. It is still random failures, but if we're taking care of all the reasons why it would prematurely fail, then we will get many years of service out of this piece of equipment, and then finally when it starts to fail because the bearing finally develops a spall or something else occurs, then we use our condition monitoring techniques to detect the problem and we plan it again as early as possible. So that's the key. We just want to keep it running in that defect-free mode as long as possible. With everything, there's an economic justification that's required. Are the steps required to improve its reliability, or let's say avoid the degradation of its inherent reliability? Can you justify that? Can you justify the condition monitoring? That they are important questions to ask. In the vast majority of situations, the answer will be yes, because those failures have a real ripple effect through the business in terms of safety, availability, the maintenance costs, and so on. So let's have a look at reliability improvement in more detail. And when I talk about reliability improvement, there's a recognition, number one, that because of the equipment we purchased, we may not have designed and purchased the best equipment for the lowest life cycle costs, but it is what it is. What we don't want to do is degrade it further through our maintenance practices and operating practices. What we want to do is run our plant with the lowest costs possible, and no, that doesn't mean we're going to fire all the maintenance people or do something silly like that. There are ways to reduce costs and increase the OEE. So we're going to reduce our costs and have the highest availability possible, and we can in turn actually increase our plant capacity as well. More we could say about that, but that's really what I'm referring to when I talk about improving reliability. So what is the condition monitoring what is the condition monitoring group's role in reliability improvement? Well, as we've discussed, we're trying to avoid the catastrophic failures, and that's a pretty simple one, and that's the general thought when people think about condition monitoring, so we won't dwell on that any further. But what we also want to do is use condition monitoring to detect the root causes of faults. Now, I'm not talking about performing root cause failure analysis. That is an important ingredient which we'll get to, but we want to detect the conditions that will result in failure, in reduced reliability, and take proactive measures. So if you think about all these factors, unbalance, issues related to poor installation, misalignment, soft foot, resonances, loose foundations, poor lubrication, poor operating practices, etc. All of those forces being applied to the machine. Poor lubricant increases the friction. Operating it incorrectly puts all kinds of loads on the bearings and seals and shaft and so on. Unbalance, etc., etc. They all result in bearing failure, reduced efficiency, seal failure, leaks and contamination, potentially fire, a number of faults. So what we need to do from a condition monitoring point of view, is detect when any of these things are going on. Detect that the machine's out of balance, or that the bearings have been installed incorrectly, or that it wasn't aligned properly. If we detect those issues and then correct them, then we are less likely to detect bearing faults. That's the aim, and that's what the condition monitoring group can do. Now, the reliability culture of the plant needs to change so that when the condition monitoring person says, I'm detecting unbalance here, and no, it's not that high that I'm concerned about the machine ripping itself apart or something like that. It's not so high that it's affecting the process or upsetting people working in a nearby office or something like that. We know though that it will reduce the life of the equipment, and there's a lot we could say about that. But people need to take notice of that. People need to act and say, we do not want to operate this machine in that state, and if an opportunity presents itself, either because you have redundancy or there is a plant shut down for another reason, if you can balance it or realign it or correct any of these issues, then you do. And there's even more we can do. For example, we can use oil analysis and wear particle analysis to check the lubricant health. We can see if it's contaminated, if it still has the correct levels of the additives, if it's got the right viscosity. We can check that the bearings and gears have been properly lubricated. We can check if there's looseness. We can check for resonance. We can check for unbalance, misalignment, bent shaft, etc. We can check if the bearings have been installed properly, if there's cavitation. All of these factors can be tested with condition monitoring, and if we correct those conditions, we will improve reliability. Now, as I said before, we're not improving the inherent reliability. We're not redesigning the machine or something like that. We're not replacing it, but we are not going to degrade it further with these sorts of issues. Now, that is still reactive, but it's somewhat proactive. We're detecting the alignment problem and then we're going to do something about it. But to be even more proactive, we want to reduce the likelihood of those problems even developing. So we are going to precision balance to G1.0. We're going to precision align the belts and shafts. We're going to perform precision lubrication. We're going to eliminate looseness, optimize tightness, minimize resonance, and improve our installation practices. And the point is, rather than detecting the unbalanced problem and then having to deal with it, if we have good balancing and alignment, etc. practices in the first place, if people have been properly trained, then these faults won't develop. Now, with some processes we can't avoid it. There might be a build-up of material on a fan. It's part of the process. We can't avoid that. Okay, we look for the unbalance and we correct it, and we clean the rotor, we clean the fan blades and balance it if necessary. Some things will develop over time. Our condition monitoring though can detect that and we can remedy it. But at all times we need to think back, well, was there a way to prevent this in the first place? So, certainly with balancing, you can perform in situ balancing, and you can balance to a very high precision so that the unbalanced forces are minimized and therefore the bearings feel less of those forces. But what's important is if you are going to do shop balancing, or you're going to have a consultant come in and do in situ or in place balancing, you must say to them, we want G1.0 and we want you to prove that that's what you've achieved. If you get blank stares, then that's a bit of a worry, and that can be the case sometimes. People don't really appreciate what that means. There's a lot of misunderstandings about that, in fact. And then, you might balance the rotor, but you have to make sure that when the machine is reassembled and the keys are in place and so on, that it is still balanced. A lot of things to understand with that. Same with alignment. People think, oh, well, I've got a laser alignment system. I am precision aligning. No, you're not. You're precision aligning only when you've defined what the tolerances are and you've achieved those tolerances. Just having laser beams involved does not mean precision alignment. Same with belt alignment. It's important that we align those belts properly. Installing bearings, there's training you can receive to understand how to do that properly and how to remove the bearings properly. Generally speaking, people do want to do their jobs properly, but they haven't been trained to do it properly, or they haven't been given the tools to do it properly. That has to change. If the bearing is installed properly, there's a far higher likelihood that it will operate for a much longer time. All of these topics we could talk about for a long time, and especially lubrication. The way the lubricants are stored and filtered and dispensed is all very important. Filtration, when contamination occurs, if it's unavoidable, using desiccant breathers or looking for other ways to reduce the moisture that's getting into gearboxes and reservoirs, ensuring that the correct lubricants are being dispensed to the correct machines and reservoirs. Bearing, the greasing process for bearings, needs to be looked at carefully, and perhaps the use of ultrasound would help. All of these things, it's not rocket science. This may involve a little bit of money to go through all of this process, but it will pay dividends. It will absolutely pay dividends. Okay, so at this point we're eliminating faults. We are detecting those signs like unbalance and so on that might lead to premature failure, and we're involved where possible with the process of making sure that we do balance properly and align properly and so on. But there's one more thing you can do, and that's involved with acceptance testing. There's an assumption in many industries that when you buy equipment, when you buy a new fan or a motor or whatever, that it is in perfect condition. It's in the ideal state for your plant. And unfortunately, that is just a mistaken understanding. It is just not true. Now, just if anyone's recognizing anything here, this is just a stock standard image. I'm not talking about this particular company. The bottom line is that a lot of companies that make fans and pumps and so on and so forth don't necessarily understand these sorts of issues themselves. The engineering process that's used to design them and construct them does not mean that the reliability will be optimal. You need to say in advance that this is what we are aiming for. You need to set the bar higher so that from a design point of view, you design for maintainability and reliability, and the procurement process can only purchase spares and replacement equipment that meets your higher standards. Because if you can make sure that you're getting quality spares and new equipment in the door of your plant, then you will have a much improved reliability picture as a result. It's really important to understand that. You shouldn't make the assumption that what you're buying is good condition. Now, what we can do then is not only set the specifications in terms of from a design point of view, if you like, but also the tests you will perform in order to prove that it has met those requirements. Now, in the simplest possible case, they can just be vibration readings. You can say, well, I will not accept vibration readings over a certain level. It should be spectrum based. You should be saying at these frequencies, these are the amplitudes. There should be no sign of any bearing frequencies, etc., etc. And we could talk much more detail about all of this. But the bottom line is you can set requirements. You can look at it in terms of testing motor rewinds and motors in general. You can test lubricants. There are a lot of tests you can do, all sorts of tests you can do. And those tests could be performed by the vendor, and they could be performed by you. Obviously that's an agreement you have to make in the first place, but you certainly have to define also how the tests will be performed, the qualifications of the person performing the tests, and so on. The idea is to reject the equipment that does not meet your standards, because not that you have ill will towards your competitors, but someone's going to get that motor or that fan that you reject, because you're saying no, it is not coming into our plant. And like everything, there's you may pay a little extra, and that sometimes is a bitter pill to swallow. But the fact is, the life cycle costs will be dramatically lower. You will be purchasing equipment with a much better inherent reliability. So if we take good care of that equipment and have the right equipment in the first place, we will achieve all of the goals of condition monitoring and improve reliability. So one challenge is, what should those standards be? How do you define what is acceptable? There are a few approaches you can take. There are quite a few ISO standards specifically designed for acceptance testing. You will also find guidelines published for the automotive industry, for the paper industry, and other industries. And then there's also the question of your own industrial experience. If you've got a condition monitoring group that has been working for a while, they should be able to say what they would expect the vibration spectrum to look like when a piece of equipment is new. Now, it's not the alarm limits they would use to warn them if there was a problem. It's, we want lower vibration than that. So there are certain things you can say, well, for this sort of size motor coupled to a pump that you're purchasing on a skid, you can say, well, I don't want to be able to detect resonance at all. I don't want to be able to detect any bearing faults. And you can go through that process, specify alarm limits, and just say, well, this is how the test should be performed, and if it's any higher than that, if the vibration levels are any higher than that, then that's a problem and you won't accept it. There's a lot more we could say about this topic, but it is very important. And so, we can ask the question, is there more we can do? Can we do more to eliminate the root causes? And really, some of what we've been talking about, in fact quite a lot of what we've been talking about, I would bundle together into the area of defect elimination. Now, it is true that we can look at the principles of RCM and how we design our maintenance program, and if we take an improved view of RCM and failure modes effects analysis, we can understand the failure modes and think about the condition monitoring tasks and so on, and we can think about maybe improvements to designs, and we can think a little more broadly about what those root causes are. But ultimately we want to stand way back and say, what can we do? And we just talked a little bit about this. What can we do from a purchasing and design point of view to make sure that what comes into our company is the best thing for our business? We have to look at the people who provide consulting services and motor rewinds and balance jobs and those sorts of overhauls and whatnot, to make sure that they all understand what our requirements are for high levels of reliability. And also, how is the equipment being transported? How is the pump or the fan or whatever it is being transported? Because we can introduce problems there as well. And then once we take responsibility, once it's inside our plant, we say, well, how are we storing it? There's a question of what spares we keep in inventory. That's an important question. But how we store them and how long we store them, that is also an important point, because we can take perfectly good equipment, put it on our shelves, and by the time we go to put it in the machine, it's no longer fit for purpose. The planning and scheduling process of maintenance has a large bearing on the reliability, and of course the way the equipment is installed also has a very large bearing on the reliability. And so it's true, this part we can perhaps say, well, it's maintenance's job to make sure that this work is done, and as I'll mention in a moment, there's more maintenance can do. But maintenance is not the root cause of our reliability problems. Yes, those practices that we've discussed are a contributor, but we have to understand it's how we operate them that has a very large bearing on the reliability of our equipment. Now, it's going to change from industry to industry, but please don't sit there and think, oh, but not in our plant, that's not an issue. make absolutely sure that that's true before you make that assumption, because in many studies that is actually proven to be the largest source of reliability issues, the reasons why equipment fails prematurely. But when we're operating the equipment, we do need to look at the lubrication process, and we need to look at all those things we talked about before, the alignment, balancing and elimination of resonance and all of that with our rotating equipment. But we can't just aim to do all of these things and assume that it will therefore be done. We need to use that acceptance testing, the quality assurance, quality control. And again, that's where condition monitoring comes in. Condition monitoring comes in a few areas, but condition monitoring to do acceptance testing, and this is another form of acceptance testing, looking at how the equipment was installed and checking, are the bearings okay, is the lubrication okay, is it balanced, aligned, can I detect resonance, etc., etc. And then, of course, on an ongoing basis, we're going to keep on performing those tests to detect failures, but also to detect root causes of those failures, lubrication problems, operation problems, alignment, balancing, and so on. And if we can do these things, then we will improve reliability. And while you have to do a cost-benefit analysis, and think about different pieces of equipment, under what circumstances do you perform acceptance testing and all of these other things we've talked about, for the majority of your equipment, it will be justifiable. And that's part of the challenge, to say, I am going to spend money to make money. The cost reduction in maintenance and operation and energy and so on will well and truly pay for it, and the increase in availability and capacity, particularly if we shorten our shutdown periods, all means we can earn more revenue. Now, you have to look at your industry and say, well, is that possible? But in majority of industries, that improved availability and improved plant capacity gives the marketing department a chance to sell more product with the confidence that you can deliver. Customers are happier, and the boardroom is happier with all the shareholders or whatever it may be. So this is an important area. And I'll just briefly mention, by the way, that on our website we have other presentations that talk about defect elimination that goes through this in a bit more detail. In fact, we have a 2.5-hour presentation available with the same title of this, but we broaden the topic and go into things in more detail to really spell out, how you do these things, where all the opportunities are, what the benefits are, and so on. So, mobiusinstitute.com, and you look for the Learning Lab, the Knowledge Base link at the top, and you'll see lots of presentations there. Anyway, so wrapping it all up, there is no doubt that condition monitoring used to detect faults is vitally important, and if you're not doing it, you need to do it, and you will see a reduction in equipment failures. But the next step is to say we want to prevent those failures by detecting the conditions that lead to it, the unbalanced misalignments and whatnot. And we have to take some action. Then we're going to use our condition monitoring skills in the quality assurance, quality control, the acceptance testing, testing equipment after it's been installed, and then ongoing condition monitoring. But we have to look at things like, the way we're operating the equipment, the lubrication and other care, cleaning it and so on. We have to see how we can engage with the operators to even perform some of these tasks, monitoring tasks and potentially lubrication tasks and other tasks that let them get more actively involved in the care of the equipment that they work with. Operator-driven reliability is generally what that's called. But then we can get into, the broader question of precision maintenance, the way equipment is installed, balancing, alignment, tightness, resonance elimination, lubrication and whatnot, how we're storing spares, what we store and how we store it, planning and scheduling, all leads to improved reliability and maintenance and maintenance practices which improves reliability, a reduction in costs, fewer safety incidences. It's obviously important. I mentioned already the transportation and storage. We can cause false Brinelling, we can cause corrosion, there's other factors there. And finally, we stop anything from getting into the plant by designing for maintenance, maintainability and reliability, and purchasing for maintainability and reliability and reduced energy consumption. We set the bar a bit higher so that yes, they can save money, but anything they purchase will give us the lowest life cycle costs. We don't save a little bit on that front end and then pay for it later with increased energy costs or repeated failures of that equipment. Well, that concludes my presentation. I hope you found it useful. You will find lots of other presentations at our website, lots of other free both recorded webinars and additional presentations that we've recorded and just put up on our website. So I hope you found it useful. Please let me know if you have any questions. If you've got any questions about this presentation, please contact me. If you're interested in our training or in our product iLearn Reliability, which provides training on all of this stuff, then please again visit our website or send us an email, and we'd love to tell you more. Thanks again for viewing this presentation.